So, hello and welcome back to the live discussions on mechanics and control of robotic manipulators. I am Isaac John. I'm a PhD scholar from IIT Palakkad. I'll be the TA who's going to handle the weekly live tutorial discussions on mechanics and control of robotic manipulators. So we are for today's uh, the today's topics will be based on the lectures or the lectures that we have seen on week two, which is mostly about the geometric modeling of serial robotic manipulators. So let's see what are the topics that we'll be covering during today's presentation. So just like what we did in the last week, the first half of the session will discuss, the topics that we have. We'll have a brief summary of the topics that we have discussed during week two worth of lectures, and then for the other half, we will solve some sample problems that will be very similar to what you can expect during your weekly quizzes. So the topics that I would like to cover for this weekend are, the kinematic parameters, used for geometric modeling of robotic manipulators. Then we will see in detail something called DH parameters. This is a method for, representing the transformation between frames attached to links of a robotic manipulator. And then we will see one method of one of the variants of DH representation. Basically, there are two variants, but for the remainder of this course, we'll be sticking with a variant of a DH representation, which is called as the non-standard DH representation. And then we'll also look into some examples, how to use this DH parameters or DH representations to fully map the kinematics of a serial robotic manipulator. So let's see what we mean by kinematic parameters. So basically, any information between two rigid bodies is basically transferred by use of frames of references. So, like for example, as you know, any robotic manipulator consists of a series of rigid bodies. For example, if I have a robotic manipulator with two links, something like this, right? We can consider this to be two links. I label this as link one and I label this as link two. And either of these links will have joints, attached at either of their ends. So maybe I'll represent these joints as J1 and J2. For example, these are pure revolute joints. They only support 1 degree of rotation about the joint axis, and the joint axis can be considered coming, out of the plane. Maybe if I depict out of plane axis using this Z axis, maybe I'll label this as Z1 and the second joint as Z2. Uh, Either of these links, link 1 will rotate about this Z1 axis and link 2 will rotate about Z2 axis. So in rigid body kinematics, we basically map, the information between any of these two links using frame of references attached to the robotic links. For example, if I attach a frame of reference like so, I'll probably call this maybe x1, y1, and z1, and maybe I'll also attach another frame of reference onto the second link, something like z2, x2, and y2. So any relationship between these two links can be transmitted by sharing the information between these two coordinate frames. So we have already seen that how do we map the pose of one frame with respect to another frame. We have seen how we can use the transformation matrices, the 4x4 homogeneous transformation matrices, and how a homogeneous transformation matrix, has information regarding the position between two frames as well as the relative orientation between two frames. So in that regard, any relative position and orientation between any of the two links can be communicated using the frames of references attached on the links, right? And for that, we will have to see, there are some conventions on how we can attach a frame of reference on each of these links. So we'll come to that, but let's look at what these points essentially say. So it says something about information between two rigid bodies. So by information, I mean the information regarding position and orientation. So the first point says the choice of coordinate frames and the locations of them. So the choice of the coordinate frame and where we are basically fixing the coordinate frame on the rigid body also plays a part in the information that is transmitted between them. For example, if you have a rigid body like this, and for representation purposes, I'll depict this portion to be the center of mass. You can attach a coordinate frame anywhere on the rigid body, maybe probably at this end, at the proximal end, or maybe at here, or maybe you can even attach a rigid body at the center of mass. But a rigid body should only require a single coordinate frame that moves with the rigid body, so that any point within the rigid body can be mapped to the frame of reference. So for example, if a center of mass is 5 units along this axis, you can actually say that, if you know the information about this frame, you can essentially say the center of mass is probably 5 units along this axis. Right? So essentially, you are representing a rigid body using frame of references. And the number of parameters to describe the information between two frames. Right? For example, if you have two frames, over here, x1, y1, z1, and x2, y2, z2, typically, how many parameters do you require, to communicate or to convey the information between these two frames? So like in the previous classes, we have seen we require 6 coordinates or 6 parameters to describe the information between two frames, right? 3 parameters for position, right? If you know the position of this first frame, you need 3 parameters, x, y, z, to locate the position of the second frame. And also, you would also require 3 more parameters, to communicate or to convey the information regarding the orientations as well, right? So typically, we would require 6 parameters, to describe the relative position and orientation between two frames. And then we also need a mechanism to use the constraints and their locations. So by constraints, I mean, what is the degree of freedom each of these frame of references have. So typically, if any two rigid bodies are floating in frames of floating in space, maybe I'll call this as rigid body 1 and this to be rigid body 2, you require 6 degrees of freedom to convey the relationship between frame 2 and frame 1. But in a robotic system or in a robotic manipulator, these two rigid bodies or any rigid bodies, any pair of rigid bodies are constrained using joints. So in this example, the rigid body 2 and the rigid body 1, their relative motion is constrained using this revolute joint. So from 6 degrees of freedom, when they were disconnected, we only end up with a single degree of freedom, right? Because of this joint, the only relative motion that is permissible is a rotation about this J2 axis. So we also need to find a method or find a way to incorporate the constraints into the kinematic modeling as well. All right. So let's check a few more other points, like as a prerequisite. For an n degrees of freedom manipulator, n plus 2 frames are required to fully define the pose of the end effector with respect to the base, right? So let me replicate the previous example. For a two-link manipulator like this one with two links, again, I'll stick with the convention of using this as the link one, and I'll call this as link two. And either of these links are constrained by pure revolute joins. And by convention, if there are n links, or if the mechanism has n degrees of freedom, you require n plus 2 frames to fully define the pose of the end effector with respect to the base. So if you consider the tip of link 2, as the end effector, because at the tip of link 2, you would be attaching a tool, maybe like a gripper, right? So obviously you need two frames attached to two of these rigid bodies, something like this. Maybe I'll call this as Z1, X1, Y1, and one more frame at for link 2, that will be uh, Z2, X2, and Y2. Notice that the orientation of these frames, 1 and 2, changes as each of these individual links rotate, right? Since the frame 1 is attached to link 1, the instantaneous orientation of frame 1 keeps on changing. And same goes for frame 2 as well. Since it is attached to link 2, uh, the orientation of position and orientation of frame 2 will change as per how the link 2 moves, right? So essentially, if you want to map the pose, which is basically the position and orientation of this end effector, all the way to a frame that is attached to the base, you would require two more frames, right? You require one frame that is fixed to the ground. That is, I'll label this as Z0, X0, and Y0, and one more frame that is attached at the tip of the end effector, like so. X3, uh, Z3, and Y3. So as you can see, for a 2 degrees of freedom manipulator, you need 4 frames. Two of them would be attached to the rigid bodies, one would be attached to the end effector, and the other one would be attached to the base, right? So for an n degrees of freedom manipulator, you will have n plus 2 frames, and they are required to fully define the pose of the end effector with respect to the base. So all the information that you have of this end effector point will be subsequently transferred through all the preceding frames all the way up to the base frame. It can go either in this direction. The chain of information can go in this direction. We call this as inverse kinematics, or it can go in the other direction. We call this as forward kinematics. So as per classical spatial mechanics principle, we would require 6 n plus 2 parameters, right? As I was saying earlier, if you have two rigid bodies in space or two frame of references in space, uh, Z1, X1, Y1, and Z2, X2, Y2, you require 6 parameters, right, to map the position, to convey the relative position and orientation between these two frames of references. But since we have n plus 2 frames, we would need 6 times n plus 2 parameters, right, to fully define the configuration of a robotic manipulator, right? So what we do with a method, we basically adopt a method called DH approach or DH parameters that would only require four parameters to convey the information between two frames. Like rather than the 6 degrees of freedom or six parameters, we would only require four parameters. So let's see what this DH approach is, and how we can implement that onto a robotic manipulator. So this DH approach was proposed by two scientists called Jacques Denavit and Richard Hartenberg. So they introduced the convention in 1955 in order to standardize the coordinate frames for spatial linkages. Like there are several kinds of serial manipulators. There are serial manipulators with 2 degrees of freedom, with 3 degrees of freedom, all the way up to 6, 7 degrees of freedom. And they have different kinds of motion, right? So with the wide variety of serial manipulators that we have, there has to be a standard method to mathematically model its kinematics, right? So these two scientists, Denavit and Hartenberg, they proposed a method so that uh, there is a standardized way to assign coordinates or frame of references into these links. So the DS parameters are four parameters, just four parameters associated with the particular convention for attaching reference frames to the links of a spatial manipulator. So like it's a convention. It's a convention to assign frames so that we would only require four parameters to communicate the information between two frames. So out of this four DH parameters, two of them are called link parameters. So they basically represent the information between two consecutive joins. And the other two parameters are called join parameters, and they represent the information between two consecutive links. So this may probably seem a bit confusing at the beginning, right? We use link parameters to convey the information between two consecutive joins, and join parameters is used to represent the information between two consecutive links. So I hope as we go through with this lecture, I hope the distinction between link parameters and join parameters would be more clear, right? With some examples. So for the time being, we leave this at this, link parameters to convey joint information and joint parameters to convey link information. Now, let's see let's see into the specifics of the DS parameters, or how, what are the, what does the convention say? The specifics of the convention. So there are two link parameters. They specify the relative position and orientation of two successive joins. Right? Link parameters convey the information, which is nothing but position and orientation between two successive joins. Right? So the first one is called link twist angle, and the other one is called link length. Right? So basically, link twist angle is essentially the angle between the previous frame, the z-axis of the previous frame, and the next frame zi along xi minus 1, right? The angle between zi minus 1 and zi along xi minus 1. And link length is basically the perpendicular distance between zi minus 1 and zi along xi minus 1. So the thing that we need to note at the moment is link parameters are something that is represented with respect to xi minus 1 axis. For example, let me show one example. If you have two rigid bodies like this, so, and one more rigid body like this. So the first joint, the joint associated with the first rigid body, I label this as rigid body 1 and this to be rigid body 2. So the joint associated with the first rigid body is vertically upward, something like this. I hope this is clear. So I label the direction of the joint as using the z-axis, something like this. So I label this as Z1. And for the second link, something like this, the direction of the joint angle is out of plane, right? So if you consider this to be the rotary joint, the axis of the rotary joint is basically coming out of plane. So I label this as, Z2. So the major distinctive feature of this DS parameters is that the first step of for what you have to do while assigning frames is that the z-axis should always be along the joint. If you have a manipulator, the first thing that you should be doing is that the z-axis corresponding to each and every joint should be along the joint axis, right? So if you have a rotary joint with an axis that is pointing upward or pointing in the vertical direction, the z-axis corresponding to that joint should be vertically up. And if you have a rotary joint that is coming out of plane, the the direction of the z-axis should be uh, along that axis of rotation. Similarly, if you have a prismatic joint, maybe I'll show one more example over here. So if this is one link, and if you have a prismatic joint, or maybe I'll do a better job. Yeah, if you have a prismatic joint like this, you can probably consider this to be a cylinder and this part to be a piston. This is basically a prismatic joint because it can only allow you this sliding motion, back and forth motion. So in robotic manipulators that have these sort of joints, a prismatic joint, the direction of the z-axis is along the joint, right? So if you want to assign a frame, the direction of the z-axis is, along the along the corresponding degree of freedom, like so, right? So yeah, the first thing what you have to do when you have a robotic manipulator is assign the z-axis along the corresponding axis, be it a rotary axis or be it a prismatic axis. That is the first thing you have to do. And we look at the first link parameter. It's called the link twist angle alpha I minus 1. So this is essentially the angle between zi minus 1 and zi along xi minus 1. So like we haven't assigned x-axis yet. We have only assigned z-axis. So maybe I'll write it over here. The first step is to assign z-axis along the joints. We have done it so far, DH, based on DH convention. And the second step is to assign the x-axis for all these frame of references. So the way to assign x-axis is that you have to look at the current axis. Maybe if you have to look at this current axis, Z1, and the subsequent z-axis, Z2, and x-axis for the current joint should be orthogonal to the current z-axis and the subsequent z-axis. So if we consider the first z-axis to be pointing vertically upward and the second x-axis to be coming out of plane, the perpendicular direction to these two directions would be along this direction, right? Should be along this direction. That will be your x1 axis. So I'll denote x1 axis like this. This is going to be our x1 axis. And to assign this x2 axis, you have to look at the orientation of z2, and if there is an z3 as well, you have to check z3, and direction of x2 would be perpendicular to z2 and z3. But for the time being, we'll consider x1, right? Because x1 is orthogonal to z1 and z2. So basically, the link twist angle is the relative orientation or the angle between z1 and z2 along x1, right? But you can actually see that z1 and z2 are orthogonal. So if I rotate 90 degrees counterclockwise along x1, z1 and z2 will be aligned, right? So essentially, link twist angle or alpha I minus 1 basically says it's the angle between zi minus 1 and zi along xi minus 1. So in this case, the angle between z1 and z2 along x1. That is what uh, the link twist angle basically convey. And now we have the second link parameter called the link length. So this is basically the perpendicular distance between zi minus 1 and zi along xi minus 1, right? So once you have aligned z1 and z2, by the link twist angle, now your z1 would look something like this. I'll represent it as z1 dash. Now link length is basically the perpendicular distance between the updated zi minus 1 and zi along xi minus 1. So if this is your z1 and if this is the z2 axis, the perpendicular distance between these two axes is called the link length. That is measured along x1. So if this is a rigid link and if the length of this rigid link is L1, right? That is essentially the link length of the mechanism. The perpendicular distance between Z1 and Z2 along X1 is given by the link length L1. So that is the second parameter, basically, is what we call this as a link length. And similarly, we have two more parameters that comes under joint parameters, which basically is conveys the relative position and orientation of two successive links along zi axis. So earlier, everything was with respect to xi minus 1, right? Relative orientation between xi minus 1, relative position between xi minus 1. And now the joint parameters correspond to the angle between xi minus 1 and xi along zi. That is the joint angle. And the joint distance is between the perpendicular distance between xi minus 1 and xi along zi. So like I'll give one example. Like if you have two joints like this, two links like this, right? So I'll attach one coordinate frame for link 1 at its end, like so. So maybe I'll denote it as this to be x1, and z1 denotes the rotary axis that is coming out of plane. So this is z1. And for the second link, x2 would be along the link length, and z2 again will be out of plane. So I'll give an example of what this joint angle means. Joint angle is the angle between xi minus 1 and xi along zi. So if this is xi minus 1 and if this is xi, or I'll call it as x1 and x2, the, the relative orientation between x1 and x2, maybe this angle, measured about z2 is called the joint angle. right? Because in the last class we have seen, you need two inputs to fully define the configuration of a two revolute as a robotic manipulator with two revolute joints. So I'll call the first joint angle as theta1 and the second joint angle as theta2. So to convey the information between the first frame x1 z1 x1 y1 z1 and the second frame x2 z2 y2, you need this joint angle, right? Because this theta2, depending on the orientation of this link, can keep on changing, right? Because as that link rotates, theta2 can basically change. What this joint angle theta, what it conveys is the relative orientation between xi minus 1, that is this axis, and xi, that is this axis, above zi, that is going to be z2. So that the relative angle is going to be theta2. And similarly, if there is an offset between x1 and x2 axis, the perpendicular distance between x1 and x2 along z2 is what we call as joint distance. We'll come back to this point, in the subsequent slides, so that we'll probably get more clarity on this. But for the time being, what we have to remember is, in case of DH representation, we only have 4 parameters rather than 6 parameters. And out of the 4 parameters, 2 of them are called link parameters, and the remaining 2 are called joint parameters. So moving on, we'll see how to assign frames on on two links, and how we can use these 4 parameters to convey the relative position and orientation between two links. So here, basically, you can see that there are two links, right? It's depicted as link I minus 1, and the other one is depicted as link I. And on the link I minus 1, you have a joint attached. This joint is attached to link I minus 1, and this entire joint is attached to link I. And these are pure rotary joints. They can only rotate about that single axis. So for the DH representation basically considers that all the links of a robotic manipulator are binary links, right? So if you have a link like so, maybe if you consider a link that can only connect to two other links, such links are called binary links, right? This is a binary link because it only has two connection points, and you can only connect two more rigid bodies to this binary link. So one link could be like this, another link could be like this. Just two links are connected to each of these, the binary link. But in case of ternary link, you can probably connect three other rigid bodies to this ternary link. And there are quaternary links with the 4 connections as well. So the foundations of this DH representation is based on the fact that the entire robotic manipulator is made up of binary links with single degrees of freedom joints, right? So even if you have a robotic arm with 2 degrees of freedom or 3 degrees of freedom or even 7 degrees of freedom, it is considered to be made of binary links, and each link has only a single degrees of freedom, either through pure rotary joint or either through pure translatory joint. So in case of a DH representation, what we do is, if you consider a rigid link like so, uh, any rigid link or any rigid link from a robotic manipulator, there are two ends to the rigid link. So if I consider this direction towards the base to be the direction of the base coordinate, I'll label this as Z0 x0 and y0. And this corresponds to the base frame, a frame of reference that is fixed to the ground. And in this direction, towards the right, you have the end effector frame, or, the gripper frame. Right? So the end, or, the extremities of the extremities of this link are called as the proximal end, PROXIMAL, and the other extremity is called the distal end, right? So the end that is nearer to the base, we call it as the proximal end, and the end or the extremities that is, nearer to the end effector, we call it as the distal end, DISTAL. So as per the modified or the non-standard DH convention, there are two DH conventions, basically the standard DH convention, and the second one is called the non-standard DH convention. And for the remainder of the course, or throughout the course, we are following the non-standard DH convention, right? So the major difference between the standard and the non-standard convention is the location where we are attaching a frame of reference, right? So in case of a standard DH convention, we'll be attaching a frame of reference at the distal end, right? Because we need a frame of reference to represent a rigid body. And in case of a standard DH convention, we'll be attaching the frame of reference at the distal end. And in case of the non-standard DH convention, we'll be attaching a frame of reference at the proximal end. So for representative purposes, I'll only use a frame of reference at the proximal end, like so. Maybe ZI, XI, and YI. Just two frames of references, just a single frame of reference. So this is the foundation, or the basic. This is how we begin getting into a DH representation, by attaching a frame of reference at the proximal end of a rigid body. So here you can see that there are two links, right? Two links, link I-1 and link I. And we begin by assigning the z-axes for the frames. So as you can see, there are two revolute joints, one along this axis and another along this axis. So the frame of reference, the z-axis corresponding to the frame of reference of link I-1, we attach it along, this joint or this axis, that is Zi-1. And the z-axis of the frame corresponding to link I, we attach it along the this rotary axis. And now what we should be doing is to find out the direction of x-axis. So basically, as per the DH convention, if you want to fix the x-axis of the current frame, maybe if I call this as Zi-1, if I have to attach the x-axis for this frame, I have to check the z-axis of the subsequent frame, this one, and the x-axis should be orthogonal to Zi and Zi-1. Should be perpendicular to both, should be a common perpendicular to both, Zi-1 and Zi. So once we have determined that, we can assign the x-axis. So I'll just represent it like so. So let this be x I-1 axis, so that Zi-1 is perpendicular to xi, and Zi is also perpendicular to xi-1. So in DS representation, we'll be only using X and Z axes. There is no involvement of Y axis, right? We need two parameters about X axis, two position and orientation parameters about Z axis, and two position and orientation parameters about X axis. Y axes are not involved. So to communicate the information between, information between these two frames, frame I minus one and frame I, we require four transformations, right? As you can see, there is, relative positional, there is a relative position between frame I minus one, right? And there is also a relative orientation between these two frames, I minus one and I. So we basically map these relative position and relative orientation differences using four transformations, which are given by, the rotation about xi minus one, xi minus one by an angle alpha I minus one. Then a pure translation about xi minus one, by an amount ai minus one. Then the third transformation is a pure rotation about theta I, about the zi axis, and a pure translation about zi by an amount di. Right. So these are sequential. You cannot mix and match the order. It has to follow these orders so that we can accommodate the relative position and orientation between these two frames. So the first transformation is a pure rotation about xi minus one axis, right? So we know that this is called the link twist angle. Link twist angle. And we use this rotation about xi minus 1 so that the relative orientation between zi minus 1 and zi, can be compensated or can be accommodated. So if this is the angle zi makes, I'll just bring this zi vector over to the zi minus 1, just for representative purposes. So if you can see this blue line, this is the direction of zi, and this alpha I angle corresponds to the rotation that you have to make about xi minus 1 axis so that zi minus 1 and zi will be aligned, right? These two will have to be aligned. So if you rotate by an amount, maybe alpha I minus 1 about xi minus 1, the orientation, the relative orientation between zi and zi minus 1 can be taken into account. So that is the first transformation, right? So once you have made the rotation, zi minus 1 will now be, oriented along xi. That is the first transformation that we'll be doing. So I label this as zi minus 1 dash, right? Because after the first transformation, that is the pure rotation about xi minus 1, zi minus 1 will now move on to this new orientation, right? That is parallel to zi. So that is the first transformation. Now we look into the second transformation. We call this the link length. So if you can recall, this is nothing but the pure translation along xi minus 1 so that the perpendicular distance between the newly aligned zi minus 1 dash and zi can be accommodated, right? So for example, if I consider L1 to be the length of this link, right? If this is a rigid link, it has to have a finite link length, right? L1, right? So if L1 is the link length, the perpendicular distance between zi minus 1 dash and zi along xi minus 1 is that link length L1, right? So once you have performed that transformation, you are essentially moving this frame, zi minus 1 dash and xi minus 1 into this position, once you have done that transformation. So I'll label it like that. Now after the second transformation, your xi would be like this, xi minus 1, I'll label this as double dash, and zi minus 1 would be like this. You are translating this zi minus 1 by an amount L1 and xi minus 1 by an amount L1. So you will end up with something like this. So this is zi minus 1 double dash. Now, the third transformation is a pure rotation about zi by an angle theta i. So we call this as the joint angle, right? So as you can see, there is a relative orientation between xi axis and xi minus 1 double dash axis. One is pointing in this direction, another is pointing in this direction, because this is a rotary joint, right? At any instance, this link can be aligned at any orientation. So to accommodate the relative orientation between xi and xi minus 1, I'll maybe call that angle as theta, right? If this is xi minus 1 double dash, and if this is the direction of xi, the relative angle between xi minus 1 and xi is, if we call it as theta I, the pure rotation about zi axis, so that the orientation between xi minus 1 double dash and xi can be matched. That is what we call as the joint angle, right? So once we do that, the position of, or the orientation of xi minus 1 will now be matching with xi. So I'll label it like so, xi minus 1 triple dash, but zi will still be the same, right? Because if you are rotating about zi axis, the orientation of zi is still going to be the same because they are lying on a same line, right? So zi double dash and zi triple dash are still going to be the same. Now after the third transformation, this is zi minus 1 triple dash and xi minus 1 triple dash. And now the only transformation that is remaining is a pure, translation about zi minus 1 axis. A pure translation about zi minus 1 axis, so that the perpendicular distance between, xi and xi minus 1 triple dash can be taken into account. So we call the final transformation as joint distance. And if there is a finite difference between these two frames, xi minus 1 triple dash and xi, if I call this as d1, if you translate the third update, zi minus 1 triple dash and xi minus 1 triple dash by an amount d1, along zi, now the final transformation, after the final transformation, zi minus 1, with fourth dash and xi minus 1 with fourth dash will coincide with xi and zi, right? So earlier we have started from xi minus 1 and zi minus 1, and using this 4 sequential transformation, we were able to end up at this location, xi and zi, just by using 4 parameters, right? So to communicate information between two frames, we have to follow this 4 transformations between any two frames. The first one is a pure rotation about xi minus 1. The second one is a pure translation about xi minus 1. The third one is a pure rotation about zi. And the fourth is a pure rotation about pure translation about zi. And you essentially know what if you multiply or post multiply each of the transformation matrices, you will end up with a transformation matrix from I minus 1 frame to the ith frame, right? Because you essentially know what these individual matrices would look like. For example, R x I minus 1 by an angle alpha I minus 1 would look something like this. It will be like 1, 0, 0 cos alpha I minus 1. Then you have minus sine alpha I minus 1. Then sine alpha I minus 1. Then cos alpha I minus 1. Then you have 0, 0. Sorry. The transformation matrix for pure rotation about x-axis should look something like this. The cos alpha I minus 1 should be here, minus sine alpha I minus 1. Yeah. Then sine alpha I minus 1, cos alpha I minus 1. Since it is a pure rotation, the first transformation is a pure rotation. The positional component will all be 0, and the final entry would be 0, 0, 0, 1. Right? And the second transformation is a pure translation about xi minus 1 axis. So that would look something like this: 1, 0, 0, 0, 1, 0, 0, 0, 1. And since it's a pure translation along xi minus 1 axis by an amount ai minus 1, it will be like ai minus 1, 0, 0. And the final row, as always, is going to be 0, 0, 0. And similarly, you can also find out the transformation matrix for the pure rotation about zi axis and pure translation about zi axis. And if you multiply all the four matrices sequentially, one after the other, you will be able to obtain this final big transformation matrix that essentially convey the relative position and relative orientation between I minus 1 frame and ith frame. So this is what the DS parameters essentially do. That is what basically a DS parameter would do. Yeah, so this is what we will be following for the course using the non-standard DH representation. Non-standard DH representation. And the important thing to notice is that we have a mixture of I minus 1 and I indices, inside this transformation matrix. And in some terms, it is only I, but in some terms, you have this I minus 1. It is basically a mixture of I minus 1 and I. But if you take a look at that standard representation, all the terms will only have the index I. There is no mixing of I minus 1 and I. But then in this course, we'll be only following the non-standard representation. This is not we are following. We won't be following this convention because, later as we go through dynamics, dynamic modeling, we will be discussing about the drawbacks of the standard DH representation. But for the time being, we'll take this as granted. In case of the non-standard representation, which is what we'll be following in this course, there is actually a mixing or a mixture of I minus 1 and ith indices. But in case of the standard representation, we'll only have index of I. So we'll see a brief comparison between the standard and the non-standard DH formulation. So in non-standard DH, the rotation theta I is around ZI axis, and the joint number is same as the coordinate number. For example, if you have a rigid body like this, you will be attaching. I'll label this rigid body as 1. And if you consider a rotary joint that is whose axis is coming out of plane, you will attach the Z axis like this along the axis of rotation, Z1, and the X axis maybe would be along the link length, X1. And what in the non-standard case, the ZI minus 1 axis and the joint number is same as the coordinate number. So if I label this coordinate Z1 X1 as coordinate 1, and if I also label this first joint as joint 1, you can actually see that everything is 1. This being the first joint, the joint number is 1, the coordinate number is 1, the link number is 1. Right? This is as per the non-standard DH representation. But in case of a standard DH representation, something like this, we have, a joint, the first joint to be here, joint 1. But in case of a standard DH representation, we will be attaching a frame onto the rigid body at the distal end, not at the proximal end. So our Z1 axis would be somewhere around here. X1 axis would be here. And over here, you have the 0th axis, the frame of reference that is fixed to the ground. So Z0, maybe X0 would be like this, and Y0 could be something else. So if this is the 0th coordinate and this is the first coordinate, in case of a standard representation, joint number is 1, but the coordinate number is 0. But in case of a non-standard case, joint number is 1 and coordinate number is also 1. Right? So this is the case of non-standard. And this is the case of standard DH representation. And we would be sticking with the non-standard representation. Right. So the second point is actuation forces, which is exerted on joint I, is also at the same place as the coordinate frame. So if you do dynamics, dynamic modeling, you would be interested to know what are the forces acting on this joint, right? So if you are interested to find out the forces acting on joint 1, you are only required to find out the forces that is acting on the coordinates Z1, X1, and Y1 in case of non-standard representation. But in case of a standard representation, if joint 1 is here, coordinate 1 is actually here. So to find out the forces acting on joint 1, you have to observe the forces acting on joint 0. So again, it's not really intuitive in case of standard representation, right? So what this says is actuation forces correspond, the forces correspond to the same joint number as well. And the third point is addressing the links, geometric characteristics such as center of gravity are more natural in the system, right? So if you have a rigid link like this, and if you have a center of gravity like this, in case of a non-standard representation, you have the frame of reference attached at the proximal end, right? So if you consider this to be the x-axis and this to be the y-axis, it is fairly easy to represent the center of gravity or center of mass with respect to this frame of reference, right? Because if you move probably around 5 units from along x-axis, you will be able to obtain the coordinates of the frame of reference as per non-standard convention. But in case of a standard DH representation, the frame of reference is going to be fixed at the proximal, at the distal end. So this is going to be your z-axis and this is going to be your x-axis. You can see that the center of gravity, center of mass, all these parameters are basically in the negative x-axis, right? Because x-axis basically points along this direction, and center of gravity is basically behind this x-axis. So we can all agree that in non-standard representation, uh, mapping all the features of a link would be more intuitive in case of non-standard. And the fourth point is in non-standard DH, there is a mix of I minus one and I indices. That is the only probably a small hiccup that we have to make, right? Because as you know, to map any to map the position and orientation between two frames, I minus one and I, you do so by four successive transformations, which is the pure rotation about xi minus one, a pure translation about xi minus one, and a pure rotation about ezi, and a pure rotation about pure translation about zi. So here you can see that there is a mixture of I minus 1 and I theory. But in case of a standard representation, that would not be the case. There will only be, you know, a single index. All right. So we'll now move on with a small exercise with a 2-hour manipulator on, how to assign, on how to assign the DS parameters. So I'll just have a brief representation of the 2-hour robot. This is one link. This is another link. And you have two joins. This is the first join. I'll label this joint as J1. I'll label this joint as J2. This can be the first link. This can be the second link. And I need two parameters, right, to fully define the configuration of this arm. So I'll call the first parameter to be, theta1. Let it be this angle. And I'll call the other angle, the second parameter to be theta2, that is this angle. And at the tip of the second link, you have the end effector, which can be a gripper. So I'll denote the coordinates of this gripper as x comma y. All right. So now what we have to do is there are four parameters, alpha I minus 1. Then you have ai minus 1. Then you have theta I. Then you have di. And if you can recall from the previous slides, the first two we call the first two as the link parameters. And the second two, we call these as the joint parameters. Right? And we also have seen that for an NDOF manipulator, for NDOF manipulator, we require n plus 2 frames. We require n plus 2 frames. All right. So based on the DS convention, we also know that we'll be attaching the frames of references only at the proximal end of the frames, proximal end of the links. So if this is the link, the proximal end corresponds to this end, and the distal end corresponds to this end. As per the non-standard DS convention, we'll be attaching the frames only on, this end. And similarly for link 2, we'll only be attaching a frame on this end, corresponding to that frame reference. So the first thing that we would do would be to find out the the Z axes of all the frames. So here, since this is a 2R manipulator, the Z axes are all going out of plane, right? It'll be perpendicular to the plane of this board or plane of the sheet. So I'll assign the first Z axis like so. This is going to be the Z1 axis. And similarly for Z2 axis, this is also coming out of plane, Z2. And now the second step is to assign the x-axis, right? So what I've said earlier is that if you are uncertain about fixing x-axis, what you are supposed to do is you have to look the subsequent z-axis, and the direction of x-axis should be perpendicular to the subsequent z-axis and the current z-axis. So if you have z1 like this and z2 like this, x1 can be perpendicular to both z2 and z1. But then since z1 and z2 are, essentially out of the plane, x1 can be along any direction within this plane, right? If you consider the plane of this board, x1 can be like this, like this, like this. Any direction is fine, as long as it's perpendicular to z1 and z2. But you will see more convenient that if you orient z1 along the direction of the link, that will be more convenient. By practice, you will get to know that if you align x-axis along the link lengths, that will be more convenient. So I'll fix x1 like so. This is going to be our x1 axis. And I'll keep x2 axis like so, along the length of link 2. Now we have basically obtained the frame of references for the two links. This is the first frame, and this is the second frame. And the remaining two frames, one corresponding to the end effector and one corresponding to the ground, you can choose it as per your convenience. It does not have to follow any convention, as per your own convenience. So in my case, I would probably stick with, Z0 again out of plane, something like I would consider the fixed frame to be like this. Z0 is out of plane and x0 is horizontal. You can fix it however you want. And the frame that is on the distal end, I'll keep it identical to the previous frame, Z2 and X2, just for my own convenience. So Z3 will be again out of plane. And X3, I'll keep it in the same direction as X2. This is going to be X3. And now I'll define the length of these links as L1 and L2. These are link lengths. We have L1 and L2. So now how do we find out the DS parameters for the first link and the second link? We have two links, and and how many frames do we have? We have frame 0, we have frame 1, we have frame 2, we have frame 3. So we'll have to find a mapping between frame 0 and frame 1. We have to find a mapping between frame 1 and frame 2. And then we have to find a mapping between frame 2 and frame 3. So in the first case, we'll consider the mapping between frame 0 and frame 1, Z0 and Z1. For the time being, you can consider, the origin of frame 0 and frame 1 to be coincident, but it necessarily does not have to be the case. But for this purpose, I'll consider frame 0 and frame 1 to be coincident. If that is the case, what is alpha I minus 1? Right? Because alpha I minus 1, I'll write it basically here. Alpha I minus 1 is the relative orientation between zi minus 1 and zi along xi minus 1. Right? So here xi minus 1 is x0 and zi minus 1 and zi are, z0 and z1. So in this case, as you can see, both of these axes are, parallel. They are already oriented. Irrespective of what configuration the robot has, even if it is at a different configuration, maybe something like this, or maybe something like this, any configuration is fine. The relative orientation between Z0 and Z1 is always parallel. You don't need any additional rotation about X1 axis. So in that regard, alpha 0 is going to be 0 because they are already aligned. And now the second parameter or the second link parameter, that is AI minus 1. So what is this AI minus 1? This is the perpendicular distance between Zi minus 1 and Zi along Xi minus 1. So in this case, we consider frame 0 and frame 1 to be coincident. We consider it to be coincident. So if they are coincident, the perpendicular distance between Z0 and Z1, this distance is going to be 0. Right? There is no perpendicular distance between Z0 and Z1. But if there was a perpendicular distance by maybe some units, you can bring that to the model. But in this case, there is no, perpendicular distance. So in that regard, AI minus 1 measured along x0 is again 0. So in that regard, we can call AI minus 1 to be 0. And now what is the third parameter? Theta I. So theta I is the relative orientation between xi minus 1 and xi along zi. Right? Relative orientation along xi minus 1 and xi along zi. So here xi minus 1 is like this, xi is like this. So the relative orientation between x0 and x1 is theta 1. Right? The relative orientation between x0 and x1 is theta 1. That is measured along z1. Right? If this is z1, if you rotate x0 by theta 1, x0 and x1 will be now, parallel. So now theta 1 for the for the first transformation is going to be theta 1. And now the final parameter d1 is basically the perpendicular distance between zi minus 1, sorry, xi minus 1 and xi along zi. So since in the first case, since they are already coincident, there's no offset that you have to move along z1. They are already coincident. So that angle is also going to be 0. And now we move on to the second case, which is the mapping between frame 1 and frame 2, right? So similarly, you can fill the mapping between frames 1 and 2, frames 2 and 3. We'll do it quickly. So in case of frame 1, Z1 axis is out of plane. In case of frame 2, Z2 axis is also out of plane. So the first parameter, the link twist, which is the relative orientation between Zi minus 1 and Zi along Xi minus 1, what would that be? So Z1 and Z2 are already aligned. You don't need any further rotation about X1 axis because they are already aligned. They are already out of plane. They are already perpendicular to the plane of the board. So in that regard, alpha I minus 1 for the second case is 0. And what about AI? AI is the perpendicular distance between, Z1 and Z2 along X1, right? So if this is Z1 and if this is Z2, the perpendicular distance measured along X1 would be given by this link length, would be given by the scalar L1. So AI minus 1 would be L1. Now, the third parameter, that is the joint angle, is basically the relative orientation between X1 and X2 measured along Z2. That is nothing but this angle theta 2. And D1 or DI is nothing but the perpendicular distance between X1 and X2 measured along Z2. But then since they are all in a plane, there is no offset between X1 and X2. So that is going to be 0. And finally, the transformation between, frames 2 and 3. So the first transformation corresponds to the relative orientation between Z2 and Z3 about X2. Again, Z2 and Z3 are all, in the same direction. So the link twist angle is going to be 0. And the second parameter, AI minus 1, or the link length, is the perpendicular distance between Z2 and Z3 along X2. That is nothing but the link length L2. And now theta, the relative orientation between Xi minus 1 and Xi along Zi. Here, at the third frame, there is no joint, right? This Z3 is not able to rotate because it's fixed to the end effector. And whatever you have over here, X2 and X3, they are always going to be oriented all the time. There is no relative orientation between X2 and X3. So in that regard, the relative orientation is, since it is 0, theta I is 0. And just like in the previous case, di is also going to be 0. Right? So you have the transformation coordinates, 0, T1. The DS parameters correspond to 0 T1 corresponds to the first row. And you have the DS parameters corresponding to the transformation between first and second frame, that is 1T2. That corresponds to the second row, and 2T3 basically corresponds to the transformation between second and third frame. So if you want to find out the transformation between the 0th frame and the third frame, you are only required to multiply the individual transformation matrices, which is nothing but 0T1 multiplied by 1T2 multiplied by 2T3. This will give you the transformation between the ground fixed frame, 0th frame, and the end effector frame, which is the third frame. So what you have to do is you have to plug in all these individual parameters into this big transformation matrices. For every subsequent transformation, you borrow the DS parameters from the DH table and you substitute that into this table. And once you have obtained all the sequential transformations, 0T1, 1T2, and 2T3, you multiply together sequentially so that you will be able to get the transformation from the 0th frame to the third frame. I hope that is clear. Now we will basically do one more example. This is like a spatial manipulator which has 3 degrees of freedom. So I'll show what this manipulator would look like. You have a base. You can consider this to be the part of a base, which is fixed to the ground. And then within this hollow cylindrical joint, you have a link of a mechanism, something like this, which can rotate about a vertical axis. If I call this as a vertical axis, the first link can rotate about a vertical axis. And to this first link, you have a second link connected by a revolute joint. So this would be a second link. So the first joint can rotate about a vertical axis. The second joint can rotate about an out of plane axis, like so. And inside the second link, you have, a cylinder. I call this the third link, which can move back and forth, inside and outside this link. So if that is the case, if this is how a manipulator would look like, how would you assign the DH frames? So the manipulator is called R parallel R, R perpendicular R parallel P, because the first and the second revolute joints are perpendicular, right? This is the axis of the first revolute joint. This is the axis of the second revolute joint, right? They are perpendicular to each other. And the third prismatic joint is actually perpendicular to the second revolute joint. I think this should be R perpendicular P, because all the joint axes are perpendicular with each other. So if this is how a robot the spherical manipulator would look like, how would you attach? How are you going to attach the DH coordinates? So as before, you have this coordinates alpha I minus 1, then you have a I minus 1, then you have this theta I, and then you have di. So as before, you can start by first assigning all the z-axes. Then later you can assign the first the x-axis. Then later you can find out the mapping between each of the frames of references. So I'll just shade this off. So we'll begin with the first link. The first revolute joint is basically a vertical joint, right? It's actually along the vertical direction. So maybe I'll fix a frame of reference somewhere around here, and I'll call this as Z0, right? You can essentially attach this Z0 anywhere along this vertical axis. If you want, you can attach it here, you can attach it here, it should not matter. As long as Z0 is along the axis of the rotation, that is still fine. So for the time being, let us attach a frame of reference Z0 here, at the very base. Sorry, we have to start attaching, it corresponds to the first joint, right? So it is Z1. And now for the second joint, since the second joint is, coming out of plane or perpendicular to the plane, I'll attach the second joint here, like so. Z2. And the third joint, since this is a prismatic joint, I'll attach the third joint, maybe something like this. Z3, along the prismatic axis. And now what can we do about the x-axis? So to first assign the x-axis for Z1, you have to look at the direction of Z1 and Z2. And as you can see, they are perpendicular, right? Z1 and Z2 are perpendicular. So x1 axis has to be perpendicular to both Z1 and Z2. So if this is the direction of Z1 and this is the direction of Z2, x1 would be like this, perpendicular to both Z1 and Z2. So this is going to be my x1 axis. And now what about x2 axis? For x2 axis, you have to look the direction of Z2 and Z3, and perpendicular to Z1 and Z2 and Z3 would be this direction, vertically up direction. So I'll attach my x2 like so. And x3 is basically a free choice, because for convenience, since that is the final axis, I can probably choose x3 like so, vertically upward. And then we also need one more frame of reference, for the ground, a frame that is fixed to the ground. So again, that is also a free choice. You can choose it however you want. And again, for convenience, I'll choose the 0th frame exactly similar to the first frame. So my 0th frame is also like so. The z-axis of the 0th frame is like so, and the x-axis is also parallel to the first axis. And now, how would you do the DH assignment? The first transformation is between the 0th frame and the first frame, right? So let's go one by one. So Z1 and Z0 are already aligned. There is no need for a twist about x0 axis. So in that regard, alpha I minus 1 is going to be 0. AI minus 1, AI minus 1 is basically the perpendicular distance between Z1 and Z0 along x0. But since they are already coincident, there is no link length parameter, that is also 0. But then what about theta I? Theta I is basically the rotation between uh, uh, the orientation between x1 and x0 measured along z1. But at this configuration, they look to be coincident, right? At this configuration, x1 and x0 seems to be coincident. But since the first joint is a revolute joint, maybe at some other orientation or some other configuration, x1 and x0 could be off at an angle, right? Maybe at some other orientation, x1 could be like this, x1 could be like this, x1, it could be anywhere along this horizontal circle, because the first frame, x1, z1, is attached to the first link that is free to rotate. But 0th axis is always fixed to the ground. So to accommodate for that orientation, we have to give a rotation θ1 about z1 so that the relative orientation between x1 and x0 can accommodate it. And then there is no, distance offset between distance offset along z1 that has to be taken care of. So now the first transformation is now being taken care of. Now, what about the transformation between the first and the second frame, 1T2? So if this is Z1 and X1, and if this is Z2 and X2, how would you map between the first frame and the second frame? All right, so now you can see that Z1 and Z2 are, perpendicular to each other, and you have to rotate 90 degrees about x1, the link twist angle of 90 degrees about x1, so that, z1 and z2 will be oriented. So the link twist angle is going to be pi by 2 radians or 90 degrees. So now Z1 would be now oriented like this, parallel to Z2. This will be Z1 dash. Now our new first frame would look something like this, Z1 and X1. Now this is Z2 and X2, right? Now what is the next parameter? AI minus 1. AI minus 1 is the distance, perpendicular distance between Z1 and Z2 along X1, right? But, we have a perpendicular distance, but there is no way we can, offset in this direction. It has to be in this direction, right? So we cannot move in this direction. So that is going to be 0. What about theta? Theta is basically the relative orientation between X1 and X2 measured along Z2. So as you can see, there is already, by default, there is already a offset of 90 degrees. X1 is here, X2 is here, an offset of 90 degrees between X1 and X2. But then since this is a rotary joint, it can also move by an amount theta, at any configuration. So the relative orientation would be now theta 2 plus 90. And then final parameter is, the distance along Z2, we have to display so that the perpendicular distance between X1 and X2 can be compensated. As you can see, X2 and X1, there is no perpendicular distance because they are intersecting. So we cannot offset the distance along Z2. But now you can see that, we actually haven't been able to realize this orientation, right? With all the 4 parameters, we were still not able to match the initial Z1 and X1 coordinates with X2 and Z2. We were not able to match. And that basically depicts, there could be some changes that can be made on how we assign the frames. Right? So instead of mounting the frame Z1 and X1 here, at the very base, we can shift Z1 and X1 to be somewhere around this point. Instead of it being this point, we can move it to coincide with this point. It's possible because we are shifting along Z1. Technically, we can shift the coordinate frame in a direction parallel to Z1. So it's not going to be much of a change. So if we do that, our Z0 would still be looking something like this. But Z1 would be like this. This is your Z1. And X1 would be like this. And X0 would be like this. So this is your Z0, X0 axis. This is your Z1, X1 axis. This is your Z2, X2 axis. And this is your Z3, X3 axis. So with that, let's see if it makes any improvement or if we can, map between 2 frames with just 4 parameters. So again, considering from the 0th frame to the first frame, the first DH parameter corresponds to the link twist angle. But since Z0 and Z1 are already aligned, there is no need for a link twist angle, so that is 0. And AI minus 1 is basically the offset along X0. That is also 0 because you don't really need to move along X0. That is 0. Theta I is going to be theta 1 because the first joint is a rotary joint. And what about di? Di is the distance that you have to move along Z1 so that the perpendicular distance between x1 and x0 can be compensated. So if I call this distance by d1, which is link length, the distance I have to move along Z1 so that the perpendicular distance between x0 and x1 can be compensated is d1, corresponding to this, corresponding to that link length. Now, what about the frame, the transformation between the first and the second frame? So again, considering the link twist angle, Z1 is like this, Z2 is like this. You have to rotate 90 degrees about x1 so that Z1 and Z2 will coincide. So the link twist angle is 90 degrees. What about the link length angle? The distance you have to move along x1 so that, the perpendicular distance between x1 and x2 can be compensated. That is going to be 0 because they are already coinciding at the same point. And what about the joint angle, theta I? That is, going to be theta 2 because if x1 is like this and x2 is like this, sorry, there is already a 90-degree offset between x1 and x2. So we have 90 degrees plus whatever additional rotation this joint will have. Because since this is a rotary joint, it can rotate anyhow it wants. That is parameterized by this angle theta 2. That is going to be theta 2. And finally, the joint distance di, that is also going to be 0. Because essentially, again, there is no distance because they are coincident. And now finally, 2T3 basically depicts the transformation between the frames 2 and 3. So again, link twist angle, let's say the link twist angle. So Z2 is like this, Z3 is like this. So they are perpendicular. So you have to rotate 90 degrees about Z2 so that Z2 and Z3 are, aligned. So the link twist angle is again 90 degrees. And now the link length angle along X2. You don't have to move along X2 because, there is no, they are already aligned in a horizontal line. So there is no need to move along X2 to make up for any offsets. And now theta is also 0 because it's a prismatic joint. It's not going to rotate about any angle. And finally, di. Di is basically the perpendicular distance between x2 and x3 measured along Z3. So if you consider this distance to be maybe d2 corresponding to the amount by which the prismatic joint moves, the perpendicular distance would be characterized by d2. This perpendicular distance. And now you substitute, each of these rows into that generalized transformation matrix, and you will be able to obtain each of these individual, transformation matrices. And once you obtain individual transformation matrices, you multiply that subsequently 0T1 multiplied by 1T2, 1T2, then 2T3. This will give you the overall transformation between 0th frame and the third frame. Yeah, that is how you would typically perform the frame assignments using the DH conventions. Yeah, now we'll see some few sample problems. There are 9 sample questions. If there is any doubt, please let me know. Otherwise, I'll just carry on. So the first question is, in a revolute joint, what are the constant kinematic parameters? So again, we have 4 DH parameters. If you know the answers, you can let me know. You can use your chat or you can use your microphone. So out of the 4 DS parameters, you have link parameters and you have the join parameters. And out of the link parameters, you have the link twist.
Link first one, no, sir.
Which one?
First one, no, sir. Answer.
So you think the constant parameters are link twist, link length,
Link,
join
join
distance.
distance, joint angle.
So all 4 are constant for a revolute joint. Is that what you think? Joined angle and then you have joint distance. So I'll just give a brief overview of what a revolute joint would look like. So, you can consider this to be a ground and you have a single link, right? Just a single link with connected by a revolute joint. All right, so I'll attach a frame of reference to the ground, something like this. Something like this. I'll have this Z0 and X0 would be like this. X0. That is that frame of reference is attached to the ground. And we should be having one more frame of reference that should be attached to this rigid body one. So X1 would be along the link length, but Z1 is also, since it is perpendicular to the ground, perpendicular to the board, Z1 would also be something like this. And the orientation, we characterize the orientation of the revolute joint by a parameter called theta1. Right? So in a revolute joint, what is the parameter that is varying? If we have a revolute joint like this, at one instance, this angle could be theta1, and maybe some other instance, it could be at some other orientation, right? So this could be maybe theta, maybe a different theta, right? So depending upon what orientation that revolute joint has, this joint parameter or this joint angle keeps on varying, right? But everything else is same. The link length is basically the same. The orientation between the 0th z-axis and the first z-axis is going to be the same. And there is no the perpendicular distance between x1 and x0 is also not going to change. The only thing that is going to change is this angle because it's a revolute joint. It varies depending on the configuration of the link. So in that regard, the only variable is the joint angle. That is the only variable for a revolute joint. Right? And as per the definition, joint angle is, the joint angle theta I is nothing but the relative orientation between xi minus 1 and xi along zi. Yes. So if your zi is z1, the relative orientation between x0 and x1 is measured along z1 is theta1. And for a revolute joint, that is the only parameter that is going to change. So the question says in a revolute joint, what are the constant kinematic parameters?
Link twist, link length, joint distance.
Link twist, link length, and joint distance. Yes, that is correct. So option C is the correct answer because all of these are going to be constants. Only variable is going to be the joint angle.
Okay, okay.
In case
Okay.
prismatic,
Yes,
I'm
sir.
sorry.
in case prismatic,
In case prismatic, what do you think that is going to be the case?
uh, in case prismatic giant, so only giant, I mean, distance will be there. Remaining are constant.
Yes. The distance along Z0 and Z1 is going to be varying. Everything else is going to be the same. So
Okay.
in case of a prismatic joint, the only variable is joint distance.
Okay.
Everything else is going to be the same. It's a constant. It won't vary with the configuration, right? So just as in the case of a revolute joint, even if the revolute joint is at a different orientation, all of these are going to be constant. It's not going to vary. But joint angle, this theta one, is the only parameter that is varying. Everything else is going to be the same.
Okay.
Okay, that is the correct answer. Moving on to question 2. A parameter is perpendicular to xi minus 1 and xi measured along zi. What is this parameter out of this DS parameter?
That is joint angle.
That is joint angle. Yes, this is exactly what we have just discussed. Joint angle is the power. No, sorry, it's the distance, right? How can it be an angle?
Okay. Joint twist.
Joint twist. There is no such thing as a joint twist. I think we have a link twist.
Link length.
We have link length,
Joint angle. Joint twist.
joint angle, and joint twist. Yes. So link twist is the angle between zi minus 1 and zi along xi minus 1. And link length is the distance between zi minus 1 and zi along xi minus 1. Joint angle is the angle between xi minus 1 and xi along zi. And joint twist is joint distance
Like
actually.
distance.
Yeah, distance is the distance between xi minus 1 and xi along zi. So in that regard, I hope we can all agree that the correct answer is joint distance. I hope that is clear enough. If there is any doubts or any further clarifications required, please let me know. So the correct answer is indeed joint distance. Now moving on to, is my screen visible though? There is some sort of latency, I suppose. I hope it's clear now.
Yes, sir.
Okay, moving on to question 3. The relative position and orientation between two successive links are represented by link twist angle, link joint
Joint
angle,
angle.
joint twist. The question actually
Is
says
it joint
relative
angle, sir?
position and orientation. It's asking both. So basically, you have joint parameters and you have link parameters. And under joint parameters, you have joint distance, and joint angle.
Angle.
And under link parameters, you have link twist
Link twist.
and link length.
Length.
Yeah, link link. So basically, the relative position and orientation between two successive links. So joint parameters have two parameters called joint distance and joint angle. So joint distance, like if you have two links like this one, right? And if I'm having a coordinate frame, if I call this as link I and this to be link I minus 1, and if this is the ZI axis, because if you consider the rotary joint to be vertical, the relative distance between these two links, measured along ZI, what do we call that? We call that as joint distance, right? This relative distance between the two links measured along ZI is called joint distance. And similarly, if there is any angle between two links, maybe if you consider this to be one link, this to be another link, and the joint is perpendicular to the plane of both, and if this is link I, and if this is ZI, the relative orientation between two links, theta I, measured along ZI, is called the joint angle, right? I hope you can see that, the relative orientation between two links is given by joint angle, and the relative position between the two links is given by the joint distance.
Joint distance.
So in that regard, the relative position and relative orientation between two successive links are
Joint
expressed by
parameters.
Joint parameter.
Joint
joint
parameters.
parameters. Yes, joint parameters. So similar logic can be applied to link parameters, right? The relative position and relative orientation between two successive joints are expressed by link parameters. I hope that makes sense now, because earlier when I said at the summary, I said it could be confusing. But now I hope some amount of clarity is there, because distance between two joints measured along ZI axis we call this joint distance, and relative orientation between two links measured along the ZI axis we call that as joint angle. So the relative position between relative positions and orientations between two joints is given by joint distance and joint angle. We call them collectively as joint parameters. So the correct answer is indeed joint parameters. Okay, yeah, I hope that is clear enough. Now moving on to question 4, it's a true or false question. It says adding a link's geometric characteristic like location of the center of gravity, etc., are easier in standard DS parameter convention.
The false statement.
That is indeed false. Because earlier what I have said is that if you have a link like this, and if you have a center of gravity, something like this, as per non-standard convention, you attach your coordinate frame at the proximal end. This is as per the non-standard convention. And as per the standard DH convention, you attach the frame of reference at the distal end. And towards here, you will have the end effector, maybe a gripper, And towards this side, you have the base, right? So if you have a coordinate frame at the proximal end, it is easier to map, interesting characteristics like center of gravity, maybe the inertia tensor, or maybe some other point of interest with respect to this frame. But if you have a frame here, as per the standard DH convention, you have to go backward. Everything will be in the negative axis. So in that regard, non-standard convention is more convenient, and this is what we are following in the course. So in that regard, addressing links geometric characteristic like center of gravity, center of mass are easier and more intuitive in non-standard representation, not in the case of a standard representation. So in that regard, the option is indeed false. We prefer non-standard DH convention.
Non-standard things are preferred in textbooks also, sir.
There are two textbooks. I've seen a case where they are preferring standard DH parameters, and in some other cases they prefer non-standard case. I don't know if you follow that robotics textbook from Crane. There is another called Crane. They follow non-standard representation, but there are a lot of fundamental introductory textbooks on robotics. I've seen a lot of textbooks that uses the standard representation. So the major thing some people are still going for standard representation is that in that general transformation matrix I minus 1 ti, there is only a single index I for the standard DH. But in the case of a non-standard representation, in case of the transformation between I minus 1 frame to ith frame, there is a mix of I and I minus 1 indices. So, this is in case of non-standard DH. Maybe this is the only difficulty we have with non-standard DH, but in every other situation, there are benefits of using the non-standard DH convention. Except for this confusion, that is only a confusion at the initial stages, but once you are used with the convention, it does not really matter if it has a mix of I and I minus 1 indices. It's not a problem at all. Right. Okay. So the answer is indeed false. Moving on to question 5. A parallelogram with ABCD, a parallelogram ABCD with coordinates 0, 0, 4, 0, 6, 3, and 2, 3 is rotated about z-axis by 90 degrees in the clockwise direction. Now the parallelogram can be described by. So what is the new coordinates of the parallelogram? After you rotate it about 90 degrees. So I'll try to have a graphical intuition regarding this. And if I consider this to be the x-axis, and if I consider this to be the y-axis, and z-axis is out of plane, and the 4 coordinates of the parallelogram are, the first point being 0, 0, I'll call this A. The second coordinate is B, that is 0, 4. This is coordinate B. And the coordinate C is, sorry, it's 4, 0, right? Yeah, it's 4, 0. It's coordinate B. And the third coordinate is 6, 3. This is going to be C. And the fourth coordinate is going to be 2, 3. This is coordinate D. Now, if you're rotating this parallelogram about this z-axis clockwise by 90 degrees, what is the new location? What is going to be the new location of these vertices? you can do this by rotation matrices, or you can do this by the transformation matrices. But how would you do that? If you want to rotate it by clockwise. So what does the 90-degree rotation about Z axis look like? How would that look like in with the rotation matrix? The rotation about Z axis by an angle minus 90 degrees would look something
0,
like
0, 0, 1.
Along the column or along the rows?
Rows, no, sir. Rows. No, sir. Top row 0, sir. Full bottom row 0, 0, 0, sir.
Yeah. Bottom row 0, 0, 0,
1.
1, something like this.
Yes.
Okay, yeah. And
And
the
top row
top
full
one would
0,
be
sir. No, sir. The
cos
last column also
minus.
0, sir. Yes,
Side
sir.
into
Yeah, I'll write it one thing. Maybe you can see if there is any mistake or not. So it will be cos of minus 90, then
sine
minus sine of minus 90, then
bottom.
sine of minus 90, then cos of minus 90, then you have 0, 0, 1, 0, 0. Yeah, I think we can probably work with a rotation matrix, right? Do we really need a transformation, a full transformation matrix? Maybe 0, 0, 0, 1, 0, 0, 0.
Not required.
Do we really need this? Because we are only concerned with a pure rotation.
Rotation. Yes, yes, sir.
Yeah. So even if you work with rotation matrices, that is still fine. So the first vector is basically the coordinate of the first vertex is 0, 0, right? So 0, 0 is always going to be 0, 0. Even if you rotate 0, 0 above Z axis, this point is still going to be 0, 0 because that is lying on that axis. But then what about this point 4, 0? So let's see what it looks like. Maybe 4, 0, then Z coordinate is 0.
0. Yes, sir.
Then the final term is going to be 1 because as per the homogeneous coordinate convention, the final term is actually going to be 1 to maintain that original scaling. So once you solve this, how does it look like? Maybe I'll simplify this rotation matrix. Cos of minus 90 is going to be 0. Minus sine of minus 90 is going to be 1. And sine of minus 90 is going to be minus 1. And cos of minus 90 is going to be 0. So if I multiply this out, I will get it as 0, minus 4, 0, 1, I suppose, right? So 4, 0 is going to be like 0 minus 4, once you rotate in the clockwise sense. So 4, 0 will come as, how did it come? Like it will come like 0 minus 4. So the new point would be here, maybe 0 minus 4. This will be your new B dash. What about the point C? 6, 3. Again, if you multiply instead of 4, 0, if I replace this 4, 0 by 6, 3, we have 6, 3, 0, 1. And if I multiply this out, I would get 3, I would get minus 6, then 0, 1. I suppose that is correct. Is it correct? So the
Last
second card. Is it correct?
Last option correct.
Last option, 3 minus 6, 0 minus 4. Okay, let us check it one by one. So the coordinate C would look something like this. The first coordinate, x coordinate is 3, and the y coordinate would be minus 6. So the other point would be 3 and minus 6. This would be C dash. And the final coordinate D would be like 2, 3, 0, 1. So if I multiply this out, we will get 3, then minus 2, then 0, 1. So you will be getting something like this. This is D dash. So yeah, something like this. So yeah, 3, I guess the final answer is indeed the correct option. If you rotate the parallelogram ABCD by 90 degrees, you will end up with something like this. Yeah, so I also agree, the final answer is going to be option F. Let's check it. Yeah, that is indeed the final answer. You can also do this, even without transformation matrix, you can still find out with just by using rotation matrix, cos theta minus sine theta, cos theta, 0, 0, 0, 0, 1. You can multiply this with the position vector as well. The reason is because all of the position vector are originating from the zeros. So like there is no component of translation involved. Every vector, vector A, vector B, vector C, vector D, all are originating from the point 0. So it is going to be a pure rotation. So instead of a transformation matrix, even if you use a rotation matrix, you will still get the same answer. Okay, now we move on to questions with DH parameters. You are given 2 frames. Find the link twist angle and the joint distance for the given frame arrangement as shown in the figure. So you are asked to find out link twist angle alpha I minus 1 and the joint distance angle di for the frame arrangement given in this question. So what is this link twist angle? What does that essentially mean? Any answers?
Z1 and Z2 along X1, no, sir?
Link twist. Link
No,
twist
sir.
is.
Yeah, yes, sir. Yes, sir.
Could you repeat?
To
I
make the
didn't-
Z2 parallel to Z1 along X1, no, sir?
Okay. Yes, correct. That is correct. So as you were saying, angle between Z1 and Z2 along X1. So what would that be?
19. Is it 90,
90 degrees. Yes. So alpha I minus 1 is 90 degrees or pi by 2 radians. What about di? What is by definition? What is di or
That's
the joint distance? Joint distance between frames 1 and frame 2.
is
How would one define that? Maybe I'll define it myself. It's the distance.
Minus 1 to x5.
Sorry.
It's actually the perpendicular distance.
Yes, perpendicular distance between x1 and x2 along z2. So here, you can consider x2 in any direction. It does not matter. Maybe for convenience you can consider x2 to be in this direction, or if you prefer x2 to be in the vertical direction, that is also fine. But here, the important thing to notice is that x2 is always going to be in the same plane as x1. Right? They are always aligned in the same plane. So there is no need for you to move along Z2 so that X2 and X1, there is essentially there is no perpendicular distance between X1 and X2. So in that regard, you don't really have to move along Z2. So that makes D2 to be or DI to be 0, basically, because X1 and X2 are lying in the same plane, so there is no perpendicular distance between it. So in that regard, what would be the correct answer? I think it should be option B for question 6. That is indeed the answer. Okay, we'll go for one more question. Question 7. Find the non-standard DH parameters. Find the non-standard DH parameters for the given frame arrangement as shown in the following figure, where frame 2 is fixed relative to frame 1. Maybe frame 2 is fixed relative to frame 1. So in that regard, there is this is not connected to a joint. It's always fixed. It won't probably move in any direction. Maybe if you consider X2 to be in this direction, there is no reason for X2 to be moved because it's always fixed. At some other instance, it won't be like this. It's always fixed. So in that regard, what are the DH parameters? We'll start by the first one, alpha I minus 1. What would that be? Alpha I minus 1. Any answers?
Vanquished.
Again, alpha I minus 1 is the angle between Z1 and Z2 along X1. So Z1 is vertically upward in the plane. Z2 is, going out of plane, perpendicular to the plane. So how much do you have to rotate along X1 so that Z1 and Z2 will be aligned? You can see it's minus 90 degrees, right? If you rotate minus 90 degrees about X1, Z1, which was originally upward, it will now be going out of plane, away from us. If you rotate minus 90, if you rotate minus 90 degrees, right? Minus 90 degrees clockwise along X1 axis. Minus 90 degrees or 270 degrees, right? 90 degrees would be like
270,
this.
yeah.
180 would be like this, 270 like this. So 3 pi by 2. So alpha I minus 1 would be 3 pi by 2. Then what about the second parameter, AI minus 1? That is nothing but the distance, or maybe I'll call it as
L2.
perpendicular distance between Z1 and Z2 along X1.
Should be L2.
Is it L2 or L1?
Should be L2, right?
Perpendicular distance. Okay, I'll do it in one more step because
Yes.
once you have rotated by 3 pi by 2, your Z1 would look something like this. This is Z1. And now the perpendicular distance would be this one, right? This distance, right? No?
Yes. Okay. Yeah, fine.
This one. This one measured along X1.
Yes. So L1, right?
That is L1, yes. So AI minus 1 would be L1. Now, what about theta I? Theta I is nothing but the angle between X1 and X2 measured along Z2, the subsequent axis. So that is, in all these cases,
be
it's
zero.
actually given 0. So that basically means x1 and x2 are, aligned, or they are already aligned. So theta is going to be 0. And the final one, di. This is the distance, perpendicular distance between x1 and x2 along z2. What would that be? So
L2.
if L2, that is indeed L2. So if this is x1 and if this is x2, the perpendicular distance between x1 and x2 measured along z2 is L2. So the correct answer is option C. No, option this one, I guess.
Minus is not there.
I think option C, right? Sorry. Yeah, option C. I think, yeah, option C. Yeah, that is indeed the correct answer. Now we move on to the final question. It's a true or false question. While performing the successive translations and rotations, we can change the order or sequence of the homogeneous transformation. Is it true or false? Maybe,
False.
if yeah, that is obviously false.
We cannot change. Yes.
Yes, because, the fundamental thing is matrix multiplications are not commutative. So A multiplied by B is not equal to B multiplied by A. So, any successive transformations, if you have a particular transformation in your mind, it has to follow that specific order. You cannot do it in any other order, actually. Just like in the case of that DH matrix, you have Rxi minus 1, then you have translation xi minus 1, then you have rotation zi, then you have translation zi. You have to follow this specific order, link twist, link length, joint twist, joint length. You cannot, do it in some other angle. It'll give you a completely wrong answer. So in that regard, while performing successive translation and rotation, we cannot, but the question says we can change the order of sequence. So that is indeed false. Okay, that is indeed false. So that's it for today's session. All the questions you can expect for the quiz are more or less similar, to what we have discussed over here. Just the only few of the things change. So like once you can solve this, these practice questions, you can easily solve the questions in the quizzes as well. So if there are any doubts, please let me know. Otherwise, we can wrap up today's session. Any further
Sixth
doubts?
question answer.
Sixth question.
Sixth question.
This one. Okay. Do you have any
Yes.
doubts in this?
Okay, sir.
If you have any doubts, let me know. We can discuss that over here. Or you just wanted to see the answer? Is that the case?
Yes, sir.
Okay. Okay. Then if there are no doubts, I guess we can wrap up this session. All right. So
Is it possible to
Thank you very
share the
much.
slides, sir?
Thank
yeah,
you,
the
sir.
slides are already shared. The recordings are also shared. Both of slides and recordings are shared. You can find the links in the course page itself. Right.
Okay,
The
sir.
recordings, everything is shared.
Oh.
You can get it from the. I may take some time for me to upload. It'll probably take some time for me to upload this recording. But once the recording is online, you can access it
Okay.
at your convenience. Okay, so thank you all for joining. we'll see next week with a different topic. So I'm
Thank you very
winding
much,
this
sir.
session.
Thank you, sir.
Thank you. Thank you. So I'm
Okay.
winding this
Thank
session. Thank you. Thank you.